we're going to be talking about types of reactions, specifically synthesis and combination reactions and decomposition reactions. In order to do those, I need y'all to make sure that you've got your lab manual and you've got the page in the back that has the rules of reactions. So if you don't have that yet, go ahead and pull that out. Or you could pull up a copy online, I guess, if you wanted to, but you need to be able to look at those rules and follow along. And I would write my notes right on those rules. I would not write them in a notebook. So go ahead and do that. If you've got your 5 different kinds of reactions, we're going only to be talking about the first 2, synthesis and decomposition. So let's just look at it briefly and try to figure out the differences between the two. Synthesis reactions are where you have 2 individual elements or 2 individual compounds, and you're sticking them together and you make some compound out of them. It could be as simple as making salt. You take some sodium, you mix it with chlorine, and you make sodium chloride. Decomposition is the exact opposite of that. That's where you're taking something that's already together and you're splitting it up. That's all decomposition is. So you can say that synthesis and decomposition are 2 exact opposites. This would be like taking salt, which we can dig up out of the ground or get from the ocean, and by using chemical processes, we can split it into sodium and chlorine. The chlorine gas is given off, which we use in plastics and lots of other pharmaceuticals, and the sodium is cool because we can make things explode, so that's good. But that's basically the difference between synthesis and decomposition. So let's go look at the rules real quick, and you guys have your rules that you can look after. Notice at the very top of your rules, it says to use the gas ion chart. Well, the gas ion chart is on that same sheet. You can go ahead and find it. It's down there at the bottom. It describes, given a given gas on the left, what ion it makes on the right. So you just know where that is. The first rule of synthesis is simple combination of elements. If you take 2 elements and stick them together, you form a compound. That's really easy. Rule number 2 is a metal oxide and water makes a base. Well, first of all, let's figure out what a metal oxide is. It's any metal, gold, silver, sodium, potassium, iron, and mixed with oxygen. So it could be iron oxide, copper oxide, whatever. And you mix it with water and you form a base. Well, here's something you guys need to know. You need to know that a base is anything that has a hydroxide in it. Anything with a hydroxide, sodium hydroxide is a base. Potassium hydroxide is a base. Copper hydroxide is a base. So anytime I tell you to make a base, you're really just making a metal hydroxide. So let's look at the balanced equation of that. So sodium oxide and water, that makes a base. The third rule talks about the opposite of that. A non-metal oxide and water makes an acid. Well, non-metal oxide could be sulfur, phosphorus, carbon, fluorine. Any of those would be good non-metals. And the oxide is just, non-metal oxide. So carbon dioxide, sulfur trioxide, nitrogen dioxide. All of those would be good non-metal oxides. And they make an acid. And you guys know from before that all acids start with H, right? So I need y'all to do me a favor, though. I need y'all to go ahead and write this note in here. I want you to write GIC. Right next to the rule, write the word GIC. And what that stands for is gas ion chart. And when we're in class, I'll say, don't forget to GIC it or GIC it or something like that. And that means gas ion chart. If you guys go down to your gas ion chart, find this puppy right here, sulfur trioxide, and tell me what ion it turns into. It turns into H2SO4 because that's the acid that it makes. You'll be using your gas ion chart here to figure out what it makes. Here's another one. Dinitrogen pentoxide and water makes nitric acid. So you guys need to be able to look at that and go, oh, okay, that's a gas ion chart. Go down to your gas ion chart, find N2O5, and tell me what ion it makes. Okay, just realize that's where you use this. An important consideration here is when we talk about fire. And when we talk about fire, like a forest fire or a fire in your fireplace or something like that, you guys need to realize there's 2 things going on. You've got pieces of wood over here, and then you've got this smoke going up, and what's in that smoke? Non-metal oxides. So you've got sulfur dioxide, sulfur trioxide, which we call SOx. You've got nitrogen dioxide, dinitrogen pentoxide, all kinds of things, which we call NOx. And you've got CO2. Those are the predominant players. All of those things, SOx, NOx, and carbon dioxide, are things that when they mix with water in the atmosphere, turn into acid. And then when the acid falls down on the ground, it produces something called acid rain. So everything that goes up in the air forms acids. Everything that stays on down here, these are all going to be metal things. These are going to be metal oxides. And we typically call this ash. And it could be sodium oxide, potassium oxide, could be magnesium oxide. All those things are found in plants, especially potassium and magnesium. In fact, they used to call the ashes from a fireplace potash, and potash is potassium oxide. And that was good because all of those things could be steeped in water. So you could take the ashes, add water to them, and you would make a base. And that base was called lye. And what's lye used for? Lye is used for making soap. So if you were an ancient frontiers person and you wanted to make lye soap, you soaked your ashes in water. You got rid of the icky part on the bottom, because there's always an icky part. You added animal fat to it, mixed it together, and you made soap. Some people who want to help their plants maybe be more acidic or more basic, sometimes will add ashes to help it be very, very basic. You have to watch what you're doing, though, because it can make it very, very basic, which is not really good for your plants. Back to the rules. The last rule is a non-metal oxide and a metal oxide yields a salt, and I'm going to want you to write GIC next to that one as well. If we look at an example of that, a salt is just a metal and a non-metal. You might want to write that up here too, so just that you can remember it. It's any metal and any non-metal stuck together. The magnesium is our metal. You can see it over here in the salt. You're going to GIC it. Carbon dioxide in the gas ion chart becomes what ion? Becomes carbonate. That's the non-metal ion. So it turns into a metal, non-metal ion. Opposite of synthesis is decomposition. So we have 5 rules here. First rule is a base, when heated, decomposes into a metal oxide and water. This is the exact opposite of one of the synthesis rules. Here's a base. You already know what a base is. We wrote that up above. And it's going to turn into a metal oxide and water. Enough said about that. Rule number 2 is the exact opposite of another synthesis rule, number 3. An acid breaks down into a non-metal oxide and water. You need to write GIC next to this one, though, because you are going to use the gas ion chart for this one. You're going to use it backwards. You're going to go from the ion, PO4, to the gas, P2O5. So just remember, synthesis and decomposition are exact opposites of each other. So just don't forget to write GIC on that one. Third rule is carbonates. There's a special rule for carbonates. They break down into metal oxide and carbon dioxide. A good example is marble or limestone will break down into calcium oxide, also called quicklime, and water. Pretty much all carbonates, when they're heated, will release CO2. And that's a good way to test. You can test for the presence of CO2 as to what kind of compound it is. But this is a very straightforward rule. You just have to remember that it turns into a metal oxide and carbon dioxide. The fourth rule, and we're getting close to being done, is chlorates. There's also a rule for chlorates. Decompose into metallic chlorides and oxygen. This is one of the methods that people used to use before there was tanks of oxygen in lots of places. They would grind up a metallic chlorate, or they would heat up a metallic chlorate and release oxygen gas, and that was a good source of oxygen gas. They also use chlorates in some fuels, like rocket fuels and for fireworks and stuff like that, because it's a stable source of oxygen to make combustion happen, to make fire happen. Potassium chlorate here is turning into oxygen. And the last rule is some things just break apart. And this is really the opposite of rule number 1 in synthesis. Just like sometimes elements come together, sometimes elements fall apart. And it doesn't have to be electricity. You guys probably need to write that in your notes somewhere. They can also just fall apart with heat sometimes. Sometimes you can heat up something like a mercury oxide and it'll split into mercury and oxygen. That's it for the rules about synthesis and decomposition. If you bring in your rules in and these examples in, and we'll go ahead and practice some in class.